Hey, hello everyone, and welcome to ACES, Advances in Cool Evolved Stars. Welcome to Monash and welcome to Melbourne. This conference is also partly sponsored by Astro 3D. The LOC would like to acknowledge the traditional custodians of the land that we're meeting on today, which are the Bunurong people of the Kulin Nation. And the Aboriginal and Torres Strait Islanders of Australia were the first astronomers here, and they have a very strong connection to the land, water, and sky, which is why we like to acknowledge their presence. So, some of you will have seen this is the schedule for the week. There have been a few last-minute changes due to unfortunate illness and a few other issues, but nothing too different to what you would have seen before. So shortly we will be starting with our first speaker, Giulia, but first I have a few more housekeeping things, which is if you still want to come on the conference excursion and you haven't yet bought your tickets, it's not too late. You still can. You can hope to try and see a spotted quoll, though they're good at hiding, which is why I put them in the picture here. You will get the chance to feed kangaroos and wallabies, so if that interests you, come along. You can use the QR code there or the URL at the top. It is almost your last chance to buy tickets for the dinner. I do need to confirm numbers with the restaurant tonight. So if you want to come to the dinner and you haven't yet purchased a ticket, please do so before the end of the talks today. And finally, we'll show this map again at lunchtime, but this is a map of where we are. We are in the Learning and Teaching building here, the orange circle, which congratulations, you've all found your way to. There are several places to eat around Monash Campus Centre. Up here in blue has a variety of restaurants, fast food to choose from. There are also a few other options. There's a Secret Garden up here and a few other shops over here. So if you're feeling lost, find someone from Monash or the LOC to show you around. But I expect there'll be a reasonably large crowd of people heading that way. Okay, when we have time for audience questions, you might see some of these microphones on your desks. If you press the button so that the light turns green, you can ask a question. If you think of a question later, please type it on the Slack. Then speakers can reply, we can have asynchronous discussions. This also applies to Zoom people. We will be allowing questions from Zoom. In case people on Zoom, please put up your hand if you have a question. Fire exits. No, there's two exits to this room, one that probably most of you came in and another one over there. The nearest bathrooms are on this side, but there are some more kind of diagonally over there a little bit further. And if you want to refill your drink bottle, there is also a small kitchen area that you should be able to see from once you walk out past those round orange seat things. Okay, so first up, we have Giulia Cinquegrana giving our first invited talk. Thanks, Giulia.
All right, good morning, everyone. Thank you very much for the introduction and the invitation to present here. So as Tysa said, my name is Giulia Cinquegrana. I'm a final year PhD student. I've been working mainly with Amanda Krakis and Alex Hager here at Monash and collaborating internationally with Maria Lagaro at Concolli Observatory and Meredith Joyce at the University of Wyoming. Okay, so the theme of this conference is Advances in Cool Evolved Stars. I spent my PhD working on the modelling side to this, in particular looking at both low and intermediate mass and massive evolved single stars. So why do I care about them being evolved? I'm interested in stellar nucleosynthesis and the origin of the elements. And the cool evolved giant stages of stellar evolution is where we see the nucleosynthetic fruit of a star's labour over its lifetime. Now, low to massive single stars only form some of the contributions to the origin of the elements. There is just only so many hours in a day and in a PhD. We also expect binary interactions to impact single star nucleosynthesis. This is Zara Osborne's expertise, who'll be presenting later today, as well as binary specific nucleosynthesis events, such as the interaction between evolved low and intermediate mass remnants like type 1As, and those between massive star remnants like neutron star mergers. And there are many other categories and subcategories here: novae, electron capture, and different types of supernovae. The key takeaway here, I think, is that the periodic table as we know it is formed by a very complex web of interacting variables on both the stellar and galactic scale, which sounds really nice and interesting until you have to invert that to figure out how each element is made, in what special circumstances, in what quantities. But those are the questions that we're asking. Some other definitions I want to revise. I'll be talking about primary and secondary nucleosynthetic contributions. So primary contributions, I'm referring to the conversion of primordial hydrogen to a heavier element, such as forming a helium-4 nucleus through the pp chain, and then converting multiple helium-4 nuclei into a primary carbon-12 nucleus. Secondary contributions or processes require that there is already some catalyst or metal present in the gas. For example, for the CNO cycle to operate, we generally need carbon-12 to begin, and to operate any kind of neutron capture or photodisintegration reactions requires that we already have the heavy nuclei in the gas around to start with. So the former increases the net enrichment of the universe, the latter rearranges the distribution of metals. So what kind of processes are we talking about? We can produce new nuclei by heavy ion fusion, so using extreme temperatures and pressures to force nuclei to overcome the Coulomb barrier. We can bypass the Coulomb barrier altogether by bombarding heavy nuclei with neutrons that have no charge. If that forms a stable isotope, then everyone's happy. If not, the neutron can beta decay, converting into a proton, and so on. If the flux of neutrons is quite low, we call this slow neutron capture. If we have many neutrons bombarding the nucleus at a faster rate than the nucleus can beta decay, we approach the other extreme, the rapid neutron capture process. Our last hydrostatic burning phases in massive stars occur under such extreme conditions that we have many energetic gamma rays flying about. So neon and silicon burning occur via photodisintegration rather than fusion, where surrounding nuclei absorb these gamma rays, they're excited to a higher state, and on their way back down, they emit a proton, a neutron, or an alpha particle. These constituents are then immediately captured by other surrounding nuclei, and abundances are eventually redistributed towards a nucleostatistical equilibrium. And lastly, stellar yields. So here we're talking about the total integrated contributions of material that a star expels over its lifetime, so the matter that's returned to the universe. This includes both material eroded by stellar winds and anything ejected by supernova explosions. For my PhD specifically, I've been looking at nucleosynthesis and mixing in metal-rich, low to massive stars. The definition of which is pretty different depending on who you talk to. So when I say metal-rich, I'm referring to anything with supersolar initial metallicities. So what's the benefit in looking at the chemical contributions and nucleosynthesis of metal-rich stars? What unanswered questions in astrophysics can we use this information to try and decipher? So one motivation comes from a galactic evolution perspective. Formation pathways for spiral galaxies and the Milky Way are still debated, and one quite difficult component to constrain is the center of those galaxies, the galactic bulge, which are typically the regions of galaxies with the highest metal content and thus proportionally the most metal-rich stars. So modeling-wise, at the galactic scale, unknown stellar features like chemical yields and final fates, so knowing which stars will explode and which won't, at appropriate metallicities restricts our prediction capabilities. Another large challenge with our understanding of galactic nuclei is the observational side of constraining these populations. These central regions are not chemically simple. The Milky Way bulge, for example, is an ecosystem with populations showing very different formation conditions requiring quite different cosmic ages. We have very metal-poor stars with high alpha enrichment, thought to be from one of the first generations. We have young, very metal-rich stars that are predicted to be the product of many generations of stellar recycling. But then we also have alpha-rich, metal-rich stars that probably need some kind of starburst formation mechanism to be able to explain high alpha enrichment with high ion hydrogen. So further than their abundances, these regions are extremely crowded and very red, making them quite difficult to see in general. Metal-rich stars in particular are cool with thick lines, which can make deriving stellar features for them quite difficult. The There has also been a larger focus on primordial nucleosynthesis and metal poor stars over the past few decades, which means that many of our methods and products are calibrated or built for metal poor regions, so they can miss important features then when they're used in higher metallicity regions. But the exoplanet community are interested in improving our understanding of the galactic bulge. NASA's Next-Gen Space Telescope, named after Nancy Grace Roman, will be directed towards the galactic center. They're betting on the fact that there are many exciting exoplanets orbiting stars there, and we do typically find a lot of exoplanets around metal-rich stars. There's a bit of debate over whether that's more correlation or detection bias, but regardless, they're there and they're ready to study. And where stars people see the negative, planet people see the positive. Extreme stellar overdensities are perfect for exoplanet searches via microlensing. So this would be a really nice opportunity to observe these stellar and planetary systems as a whole to try and shed some light on the star-planet connection. And when paired with improved theoretical predictions across the mass and appropriate metallicity spectrum, we hopefully also improve our understanding at much larger scales, the galactic. More so than just deciphering the galactic center, from a stellar theory perspective, studying metal-rich nucleosynthesis and mixing helps us to understand how these stars are contributing further to the enrichment of our universe. We know that as gas becomes more enriched, it's much cooler, and so we're more likely to form lower mass stars. Stellar evolution, as a basic necessity, requires stars of a large enough mass to be capable of higher order fusion, at least to produce a diversity of elements. So enrichment will hamper stellar processes at some stage, but what stage is that? Now, we've somewhat characterized the starting order of contributors and polluters in the universe in terms of core collapse supernovae and the delayed onset of type 1As. What's everyone's role in terminating the process? Who cuts off their contributions to the universe first? So these are some of the questions and motivations that have been swirling around in my head for the past few years. And today I want to highlight some contributions that I've made to this topic during my PhD, which has really been dedicated to understanding stellar processes at these higher metallicities. So I want to give you an idea of what we've found in these two mass regimes and what that indicates for the place of metal-rich stars in the context of galactic chemical evolution. I'm going to take a quick water break. Okay, so we'll start off with the low and intermediate mass range, roughly 1 to 8 solar masses. And for our grids, I'll be talking about initial metallicities of solar to about 7 times solar. So to highlight a few key features of low and intermediate mass evolution, they don't explode on their own. Their contributions to the universe come from the erosion of their envelopes via stellar winds. And remember that nucleosynthesis occurs in the dense interior region that will become the white dwarf remnant, not normally the convective envelope. So just based on a given process occurring in a low mass star, there's no guarantee that we'll actually see the products of that reaction return to the universe. We do, though, have a few opportunities for mixing between the interior and the surface, which we can then observe. And these are the large convective dredge-up episodes that occur on the giant branches. So I'll talk more about these in a minute, but I want to note that the efficiency of each dredge-up event are optimized for particular mass and metallicity ranges. So some unlucky stars in that range will not experience much mixing at all between their interior and their envelope, and in their dying days, they'll be expelling material close to their initial composition, relatively unprocessed. So how, when, if these dredge-up events occur is really important for understanding stellar contributions to chemical evolution. For low mass stars, core burning phases are restricted to hydrogen and helium, with some degenerate carbon burning in intermediates, but we're not going through all the higher order burning stages leading to core collapse. Instead, once core helium is depleted, we ascend a second giant branch, the asymptotic giant branch. So at this point, we have an inactive degenerate carbon-oxygen core, and further core contraction is going to ignite helium burning in a shell surrounding the core. We also have a hydrogen burning shell at this point. So for low and intermediate mass stars, post-core helium burning time is spent on the asymptotic giant branch with an inactive carbon-oxygen core and intermittently burning double hydrogen and helium shells. So we enter the early AGB first after core helium depletion. The y-axis here is a proxy for the thickness of the helium shell, the x-axis time along the AGB, first the early AGB and then the clumpy bit at the end is the thermal pulses. So along the early AGB, the helium shell burns itself thinner in mass. Eventually, it's so thin that an expansion will result in some decrease in pressure, but not a drop in temperature. So this is known as the thin shell instability. and it occurs roughly at 0.25 on these plots. So once the shell thickness drops below this limit, burning will continue in both shells for a little bit of time, amplifying the pressure until it's finally released in a thermonuclear runaway, or thermal pulse. So this begins the thermally pulsing phase of the AGB. After a thermal pulse occurs in the helium-burning shell, the energy released from it goes into expanding the outer regions of the star in one of these big dredge-up events. And the dredge-up events that occur after thermal pulses are known as third dredge-up events. The first two occur prior to the thermally pulsing AGB. They only occur once, second dredge-up only in intermediates, and they only mix the products of hydrogen burning to the surface. So they're not super interesting. The third dredge-up is particularly special because it dips into regions of prior helium burning and slow neutron capture nucleosynthesis. It can also potentially occur after each thermal pulse, which, depending on initial mass and metallicity, can be tens to hundreds to thousands of pollution events in super AGBs. So even though we're not doing fancy supernovae high mass explosions, through this mixing event, low mass stars really start to contribute to the origin of many heavy elements on the periodic table. Observation suggests, however, that the efficiency of this third mixing event decreases with initial metallicity. So if we look at barium-enhanced stars, for example, which we predict are binary systems where the more massive star has shot through to the AGB first and then dumped its AGB process material onto its companion, and we're observing the companion. So metal-rich barium stars typically show lower enhancements in slow neutron capture products. We can also look at population statistics of evolved stars, using carbon-rich evolved AGBs as proxies for efficient dredge-up, and then calculating across a galaxy the rate at which carbon stars, and thus efficient dredge-up, occur in a region as a function of the galactic metallicity gradient. So here too, we find that carbon stars are less common in high metallicity regions. So focusing on the thermally pulsing AGB, what do we see in our models? As giants, metal-rich stars are always cooler and less luminous than at solar metallicity. Opacity increases in low mass stars with initial metal content, and so they're much puffier and less dense. As a result, we see that these metal-rich models endure less efficient thermal pulses. So again, thermal pulses occur due to the thin shell instability, but because metal-rich models have helium-burning shells that are less dense, the resulting thermal pulses, if they now occur, are less extreme. So on the one hand, you could say metal-rich stars are bad at thermally pulsing, or take the glass half full approach that they're just better at maintaining thermal stability. Metal-rich stars also have higher rates of mass loss, which means they go through less thermal pulses overall. Now, on the other side of these less extreme thermal pulses is the third dredge-up. So the x-axis here is thermal pulse number, which is roughly time on the thermally pulsing AGB. And the y-axis represents the amount of material mixed from the interior region into the convective envelope. So at 0, nothing's mixed. At 1, all new products that have been formed during the previous interpulse period are mixed up into the envelope. So very successful mixing. Each curve is a different metallicity. All models are 3 solar masses. So with weaker thermal pulses, there's now less energy to go into expanding the outer regions, and the efficiency of what's mixed into the convective envelope severely declines with increasing metallicity. So the most metal-rich model is actually flatlining at 0 here. The next model at twice solar metallicity, the red shaded area, is the smallest area under the curve. So we see less primary carbon, less S-process products on their surface with increasing metallicity. And there's another hiccup for neutron capture. So the free neutron source in low mass stars is mostly primary, which means that regardless of whether we have a solar metallicity model or a 5-time solar metallicity model, we'll have proportionally the same number of free neutrons. The supersolar metallicity model, though, will have many more iron 56 nuclei floating about, which are the most common neutron capture seeds. So that same pool of neutrons is now diluted over more heavy seeds, leading to the formation of lighter neutron-rich isotopes. Then pair this lower S-process efficiency with the lower efficiency of dredge-up in metal-rich models, and things really start to look a bit dire for neutron capture at high metallicities. Our intermediate mass cases are roughly 4 to 8 solar masses. So although the third dredge-up is very metallicity dependent, the second dredge-up on the early AGB is a bit less so. So our intermediate mass metal-rich models actually become quite enhanced in hydrogen-burning products as a result, like nitrogen-14. But noting that this nitrogen would be secondary. So we're just rearranging the carbon-12 that we were born with into nitrogen-14. Lower metallicity intermediate mass AGBs can produce primary nitrogen at the base of their convective envelopes in between thermal pulses. Temperatures here need to be pretty high, and primary carbon needs to have been mixed into the envelope beforehand if we want primary nitrogen. In our metal-rich models, the density profile at the base of the envelope is too cool for this, and we already know they endure less efficient dredge up. So primary nitrogen is not a strong prediction from our models. Now, let's move on up in mass. So here I want to look at the progenitors of type 2 core collapse supernovae. We're skipping the region in between the super AGBs that may be massive enough to explode the electron capture supernovae. Our stars are massive enough to avoid the super AGB. They proceed through all the normal higher order burning stages until they hit the Chandrasekhar mass and collapse. We're most interested in the ones large enough to collapse to a neutron star, but not so large that everything just collapses into a black hole. This means we get the chemical yields from the eroded envelope, plus the dense interior, which may have been explosively processed. Final fates in terms of neutron stars versus black holes are not monotonic, but in general, we get more neutron stars at lower masses, and at some mass threshold, we're only going to get black holes. Black holes are just a little bit less interesting nucleosynthesis-wise, because we don't get the core nucleosynthesis. We just get whatever's been eroded prior to collapse. So how do we model this? We're evolving a progenitor in 1D from the zero-age main sequence to the pre-supernova stage. For the models that we predict do undergo a supernova, and we base that on their stellar structure, we blow them up using a piston and then follow how the shockwave propagates through the hydrostatically processed material. So what does the resultant nucleosynthesis look like then in our metal-rich massive models? So these are the yields from some of our supernova progenitors. Proton number on the x-axis, abundance on the y-axis, and I've just plotted some 18 solar mass models for a variety of different metallicities. So during hydrostatic burning, there are a few significant impacts of metallicity. Alpha elements are formed during helium and carbon burning for the light species, oxygen burning for the heavier isotopes. But we see a decreasing production of alpha elements with increasing metallicity, but an increasing production of odd Z and weak slow neutron capture elements. So odd Z elements can be produced during helium and carbon burning. Most of the abundant odd Z isotopes are neutron rich. For a nucleus to be stable, it really likes to have even numbers of both protons and neutrons. Odd proton or odd neutron numbers can be okay if they're paired with an even number of the other. It's just odd-odd that we really want to avoid. I think I went too far. Okay, so our odd Z elements with odd proton numbers really like to have even neutron numbers, which means they will generally have more neutrons than protons and be neutron rich. And our metal-rich models provide better conditions for this than metal poor models. We start with a lot of C12 in our gas. During hydrogen burning, much of this C12 is converted into nitrogen-14 because it's the slowest reaction and it bottlenecks the CO cycle. During helium burning then, we have lots of alpha particles flying about, helium-4 nuclei. This nitrogen-14 can capture some alpha particles leading to neon-22, which then becomes quite a good source of free neutrons. So this is a secondary source because it scales with metallicity. The more carbon-12 we start with, the higher the initial metallicity, the more neon-22 we end up, the more neutrons. So it shouldn't be a massive surprise then that we see the production of these neutron-rich isotopes increasing with metallicity. This also has implications for heavier element production by the slow neutron capture process. So same method as we talked about previously, but rather than forming these heavy neutron-rich isotopes, we're forming mainly between atomic numbers or proton numbers of 30 to 40. So this is called the weakest process, the strongest process for our low mass stars. But unlike in our low mass stars, this free neutron source is now mostly secondary, and so the amount of both neutrons and iron-56 seeds increases with metallicity, and the production of weakest process elements increases with metallicity. Okay, are you able to press play? Sorry, I thought I'd have it in front of me. Okay, cool. So let's fast forward a bit through the collapse and the formation of the shockwave to the point at which the shockwave is moving through our hydrostatically processed shells. So if the shock can make it through a given region, maintaining pretty high temperatures, we can see some explosive burning, by which I mean that nuclear reactions are occurring at rates faster than the dynamical timescale for expansion. So this is the start of the shock propagation through a 15 solar mass, 6 times solar metallicity model, so very metal rich. X-axis is mass coordinate, where we're focusing on what used to be the hydrostatically processed carbon and helium burning shells. The y-axis shows mass number, just up to 100. And so as explosive burning occurs throughout this region, throughout the shock passage, abundances on the y-axis will be redistributed. So the main impacts of metallicity at this stage will be on our pre-supernova structure. So it will affect the path of the shock wave and also the initial, and by initial I mean pre-supernova abundances in each shell. On nucleosynthesis itself, the largest impacts of metallicity are on the secondary processes like photodisintegration and further neutron captures. We build a lot of heavy nuclei with hydrostatic weak S process, and now we're starting to break down those nuclei. So where we're turning purple. All right, and yes, many of these nuclei are then redistributed towards tighter bound lighter species. Okay, so this is the same model, just showing before and after some abundances. The pre-supernova abundances are the dashed lines. So due to these processes, we have the formation of a variety of P nuclei or proton-rich isotopes of molybdenum, barium, cerium, etc., formed by taking away a neutron with photodisintegration. And we have the formation of some neutron-rich isotopes that love to grab those neutrons. So if we zoom out, that's where we were. Particularly, we see some production of germanium, selenium, and krypton that are quite skilled at capturing any 3 neutrons being thrown around. So although at low and intermediate masses, the nucleosynthetic contributions of metal-rich stars are a little bit bland, things start to look more colourful at higher masses. But as I said previously, metal-rich stars are the end products of chemical evolution. And it looks like this might be a last burst of colour in the single star range. So although we build more secondary neutron-rich and proton-rich isotopes with increasing metallicity, mass loss rates really step up at the same time. The upper mass threshold for type 2 core collapse supernovae at higher metallicities kind of mirrors that at low metallicity, but not because they're forming such massive cores that they're just collapsing directly to black holes. In the supersolar metallicity case, mass loss gets so extreme that as we increase mass, our whole envelope is being ripped off during core helium burning. So this means our star doesn't follow its typical evolutionary path through all the burning stages. It will undergo a different path, probably leading to a type 1bc stripped core collapse supernova situation. So different nucleosynthesis game. So our metal-rich type 2 core collapse progenitors are still coming up against the limits of chemical enrichment and stellar evolution. And depending on how strong the mass loss is, this could shift the metallicity threshold at which we're likely to realistically see the impact of these processes. So in other words, this is kind of the ideal case of what nucleosynthesis could occur, but stellar evolution might get in the way of our stars actually being able to reach that point. So to summarize, at lower masses, stars born from more metal-rich gas will experience weaker thermal pulses, which cause much less efficient third dredge-up mixing. These are not great sources of primary carbon. Free neutron sources in low mass stars are mostly primary, and given that metal-rich stars have more ion seeds in their gas, they produce lighter neutron-rich species. And then they struggle to mix those lighter species into their envelope. So they're also not great sources of S process, a strong S process. At intermediate masses, stars produce decent amounts of secondary hydrogen burning products like nitrogen and sodium. They do not produce a lot of primary nitrogen. We do still get some weak S process though in these intermediate mass models. Okay, so massive metal-rich stars really battle their mass loss rates. If they can make it to the pre-supernova stage, they will have formed less alpha and more odd Z elements during hydrostatic burning. The free neutron source in massive stars is mostly secondary, so because the amount of neutrons now and iron 56 seeds both increase with metallicity, our models become quite efficient producers of weak S process elements. So this means that they have a lot of heavy nuclei still around post-collapse, and so secondary processes like photodisintegration and further neutron captures can form quite a bit of proton-rich and some more neutron-rich nuclei. As a population then, as metallicity increases, we see less carbon, alpha and strong neutron capture elements, more odd Z and weak slow neutron capture elements. And we find that further enrichment is kind of being squeezed into this proton number range of about 11 to 40. So I'll leave it there, thank you.
Thank you, Giulia. Excellent talk. Does anyone have any questions for Giulia? I have one to start with. So you mentioned that higher metallicities result in higher mass loss rates. Is that something that can be like quantified within an equation or anything?
Well, I guess it depends on how you treat your mass loss. So, I mean, in general, these stars are puffier and less dense. The fine details of how mass loss works is not my expertise. So, I guess from my level, I'm not super sure.
Okay, thanks. Any other questions?
Hello. Oh, okay. Yeah, good talk, Giulia. So your work is fairly predictive, which I respect, but I'm wondering, do we know currently in the observed stars what the distribution of, say, like mass and metallicity is? So, right, high mass stars should be higher metallicity, but do we have like a relatively well understood understanding of that distribution?
Do you mean specifically the link between mass and metallicity? Like the formation of...
No, I mean, like in the current galaxy, do we know like roughly what metallicities higher mass stars should span versus like lower mass stars?
As a function of mass, I don't think so.
Okay.
We know generally like what metallicity ranges span the galaxy.
Okay.
I thought that was going to be your question.
Sorry.
Like, where are these stars going? So we find stars in the galactic bulge approaching iron to hydrogens or M to H's of up to, we find quite a lot at like 0.04, 0.05. And there's one paper that kind of extends further than that, which has pretty high metallicities. So that's where we really start to come up against this barrier of the massive uncertainties and the kind of unclear observations. So I guess maybe that kind of answers your first question, that in terms of strictly observations, it's quite difficult to constrain these things at high metallicity. I hope that answers your
that's
question.
good.
Any other questions? So with the different metallicities, you sort of hinted that lower mass massive stars might not actually reach the supernova phase. Do we kind of know the cutoff for that?
Quantitatively, no. We have a lot of like qualitative suggestions. So we typically find much more Wolf-Rayettes in metal-rich regions, which is what we would expect to see if they're not making it all the way to the pre-supernova stage. But quantifying the mass at which stars are exploding is really difficult. There's a bunch of different ways you can do it, but we kind of end up with this small, at least through my reading, you end up with a small number statistics problem. So the actual boundaries are quite rough. We would, rely more on the qualitative patterns.
Anyone else have a question? Oh, we have a Zoom question. Maxime, you can unmute yourself and ask.
Thank you very much for a nice presentation, Giulia. I've been wondering if there is anyone, if you have any plans on exploring how the binarity impacts your results that you have presented.
Yeah, that's a really good question. I would love to, but I mean, some of our other students are already working on that. So Zara, for example, is taking the yields that Amanda has made and incorporating them into binary C to basically look at the impact of, say, What would binarity do to the formation of carbon stars or barium stars? So I'm very interested in that question. I'm not sure whether I will be doing that myself or I can rely on my very smart colleagues to do that.
Thank you very much.